In this video, we are going to talk about how to find the solution of a system of linear equations by using Gauss Jacobi Iteration Method. We shall understand this method by solving a question. So the question is, find the solution of system of linear equations correct to one decimal place. So we have three linear equations in three variables x, y, z, and we have to find its solution. Since we have to find a solution correct to one decimal place, so for now we will fix our calculator up to two decimal places. So we know that solution of a system of linear equations by Gauss Jacobi Iteration method exists only if the system is diagonally dominant. So we will check that first. Let's look at this system of equation. If we can write this in the form of a matrix 9, 2, 4, 20, 1, 10, 4, 6, 2, minus 4, 10, minus 15. And the diagonal elements are 9, 10, 10. So for diagonal dominance, the first diagonal element 9 absolute should be greater than the sum of the two coefficients in that equation, and absolute sum, meaning that absolute 2 plus absolute 4 means these two coefficients. And now in the second equation, the diagonal element is 10. Its absolute should be greater than sum of the other two coefficients, meaning that 1 and 4. Absolute 1 plus absolute 4. And in the last equation, the diagonal element is 10. Its absolute should be greater than sum of the two coefficients in that equation. So in the third equation, you can see that 2 and minus 4 are the other two coefficients. So absolute 2 plus absolute minus 4. If all these conditions are true, we will say our system is diagonally dominant. So first inequality gives us 9 absolute should be greater than 6, which is true. Next inequality gives 10 absolute should be greater than 5, which is true. And the third inequality gives 10 should be greater than 2 absolute is 2 minus 4 absolute is 4, so it should be greater than 6, which is also true. Since all these conditions are true, so it means that our system is diagonally dominant. So now we can start finding the solution by Gauss Jacobi Iteration method. So to start finding the solution of the given system of equations, first we will separate out the diagonal variables. What do I mean by diagonal variables? Remember that 9, 10 and 10 are the diagonal elements. So the variables along with these coefficients are the diagonal variables, like x, y and z in these three equations are the diagonal variables, so we will separate them out. So looking at this system, the first diagonal variable is x. We'll keep it out and take everything else on another side. Gives us 20 minus 2y minus 4z whole divided by 9. From the second equation, the diagonal variable is y. We will write it on the side. Everything else on another side gives us 6 minus x minus 4z whole divided by 10. Now from the third equation, we have to separate the variable z, which we are calling the diagonal variable. It gives us z is equal to minus 15 minus 2x plus 4y whole divided by 10. Now that we have separated out the diagonal variables, we are going to put this system in the form of iteration. So we will write xn plus 1 is equal to 20 minus 2yn minus 4zn whole divided by 9. So on the left hand side, we have put the subscripts n plus 1, and on the right hand side we have put the subscripts of the variables y and z as n. So we have done that. So if we put the previous values of yn and zn, then we will get the latest value for xn plus 1. The same way, let's put the second variable in the form of iteration, which is yn plus 1 equal to 6 minus xn minus 4zn whole divided by 10. And the last variable is zn plus 1 is equal to minus 15 minus 2xn plus 4yn whole divided by 10. Now that our system is in its iterative form, and remember that in this iterative system, n is running from 0, 1, 2, 3. We are calling this system as A so that we can refer to it whenever we want. To start the process of iteration, we will put n equal to 0 in the system A. When we do that, look at this equation. When we put n equal to 0, it gives us on the left hand side 0 plus 1 is 1 x1, and on the right hand side we get 20 minus 2 y0 minus 4 z0 whole divided by 9. And we get y1 equal to 6 minus x naught minus 4z naught whole divided by 10. And we also get z1 equal to minus 15 minus 2x naught plus 4y naught whole divided by 10. Now please see that x1, y1 and z1 depend upon y0, z0 and x0. So to find x1, y1, z1, we need the starting values, meaning that we need the values of x0, y0 and z0, initial values of these variables, and we can assume that the initial values are 0, 0, 0. You can assume any starting values of these variables, but for simplicity we are assuming that x0, y0, z0 is 0, 0, 0. Let's plug these values x0, y0, z0 in x1, y1, z1 and see what do we get. So for x1 we get 20 minus 2 into 0 minus 4 into 0 whole divided by 9, which gives us 20 by 9, and in your calculator you will see that it is 2.22. The same way we find y1 equal to 6 minus 0 minus 4 into 0 whole divided by 10, and it gives us 6 by 10, which gives us 0.6. We find z1 by plugging the value of x0 and y0 as 0, 0 on the right hand side gives us minus 15 by 10, which is minus 1.5. Now that we have the values of x1, y1 and z1, we can use these values to find the next iterative values. So x1 is 2.22, y1 is 0.6 and z1 is minus 1.5. Now we got the values of x1, y1, z1 by putting n equal to 0 in the system A. For the next iterative step, we are going to put n equal to 1 in the system A. So our given system A is this. And when we put n equal to 1, so look at the first equation, it gives us x2. So we have x2 as 20 minus 2y1 minus 4z1 whole divided by 9. y2 is 6 minus x1 minus 4z1 whole divided by 10. We have z2 as minus 15 minus 2x1 plus 4y1 whole divided by 10. Now please look at x2 and its right hand side. If you plug the values of y1 and z1 on the right hand side, you will be able to get x2. So let's do that. 20 minus 2, y1 is 0.6 minus 4, z1 is minus 1.5 whole divided by 9, and this gives us 2.76. And now for y2, 6 minus x1 is 2.22 minus 4, z1 is minus 1.5 whole divided by 10, and it gives us 0.98. For z2 we have minus 15 minus 2, x1 is 2.22 plus 4, y1 is minus 1.5 whole divided by 10, and it gives us minus 1.70. So now we have x2, y2, z2, which are 2.76, 0.98 and minus 1.70. So by putting n equal to 1 in the system A, we got x2, y2, z2. We are going to put n equal to 2 in system A to get x3, y3, z3. So when we put n equal to 2 in the system A, we get x3 as 20 minus 2y2 minus 4z2 whole divided by 9. y3 is 6 minus x2 minus 4z2 whole divided by 10, and z3 is minus 15 minus 2x2 plus 4y2 whole divided by 10. And when we plug the values of x2, y2, z2 in these three equations, we get x3, y3, z3. So let's start with finding x3. 20 minus 2, y2 is 0.98, minus 4, z2 is minus 1.70, whole divided by 9, which gives us 2.76. For y3, we have 6 minus 2.76 minus 4, z2 is minus 1.70, whole divided by 10, and it gives us 1. For z3, we have minus 15 minus 2 into 2.76 plus 4 into 0.98 whole divided by 10, which gives us minus 1.66. So we can see that we got x3, y3, z3, which are 2.76, 1 minus 1.66. Now we have to check that should we stop here or not. Look at the values of x2, y2, z2 and x3, y3, z3. When you compare x2, y2, z2 with x3, y3, z3, you can see that x2 and x3 are exactly same. y2 and y3 are not same, but they are close. The same way z2 and z3 are also close. So when the previous set of values start looking similar to the latest set of values, that's when you have to check the stopping criteria, meaning that you have to check the differences. Let me calculate the difference of x3 with x2, x3 minus x2, an absolute difference. So we can see that it is 2.76 minus 2.76, which is 0.00. So we are trying to find the solution correct to one decimal place, meaning that on the right of decimal in this difference there should be 1 0 and second could be any digit. But in the first difference of x3 and x2 we got 2 zeros, which is a perfect situation. But all the three variables differences should have on the right of the decimal 1 0 and a digit. So we have already checked x3 minus x2. Now we will check the difference of y3 and y2, which is 1.00 minus 0.98, and absolute difference is 0.02. In this difference also on the right of the decimal there is a 0 and a third digit, which is what we are looking for. So this also holds. The first difference also holds up to the criteria. And now we will check the third variable difference, z3 minus z2, which gives us minus 1.66 plus 1.70, which gives us 0.04. So in the case of the third variable, the criteria holds, that is on the right of the decimal there is 1 0 and a digit. So if all these three conditions hold, so we can say that x3, which is 2.76, y3, which is 1.00, and z3, which is minus 1.66, represent the solution of system of given linear system of equations correct to one decimal place. We can also do the verification that these x3, y3 and z3 are actually the solution of the system of linear equations. To do that, we will plug x3, y3, z3 in the places of the variables x, y, z in the given system. So we have the first equation as 9x plus 2y plus 4z equal to 20. So here in the places of x, y, z, we will put x3, y3, z3. So we will have 9, 2.76 plus 2 into 1 plus 4 minus 1.66 equal to 20. So this was the first equation where in the places of x, y, z we have plugged x3, y3, z3. This left hand side should be equal to 20, and when we look at the calculations on the left hand side, we will see that this is equal to 20.20, which is approximately equal to on the right hand side as 20. So for the second equation where we have x plus 10y plus 4z equal to 6, in the places of x, y, z we will plug x3, y3, z3 and we will get 2.76 plus 10 into 1 plus 4 into minus 1.66 equal to 6. When we do these computations on the left hand side, this is equal to 6.12, which is approximately equal to 6. And the last equation was 2x minus 4y plus 10z equal to minus 15. So in the places of x, y, z, we will plug x3, y3, z3 and we get 2 into 2.76 minus 4 into 1 plus 10 into minus 1.66 equal to minus 15. When on the left hand side we do computations, we see that this is equal to minus 15.08, which is approximately equal to minus 15 on the right hand side. So yes, we can see that x3, y3 and z3 are the solutions of the given system of equations correct to one decimal place by Gauss Jacobi Iteration Method. So in this video, we have looked at finding the solution of the system of linear equations by using iterative method, that is Gauss Jacobi Iteration Method. And in the next video, we will look at finding the solution of a given system of linear equations by using another iterative method, which is Gauss Seidel Iteration Method.